This video contains the solutions for 28 to 32, your Physics C Mechanics Practice Test number 2. Number 28, we've got a block that's being pushed up against a wall here, and with a force F, its mass is m, coefficient of friction between the block and the wall is u, or mu, I should say, and what value of F is necessary to keep the block from slipping down the wall? Well, remember, the normal force here would be pushing back. Let me draw a free body diagram here. F would be going this way, right? Drawing it from the center here. The normal force would be here. And then the frictional force, if this were going to move, it would move this way, right? It would slide down. That means the frictional force is up, and gravitational force is down. So let's see, if we want to keep it from slipping, the frictional force has to match the gravitational force. So we want to do frictional force. It needs to at least match the gravitational force. If it's more, then that's great, then it's not going to fall. So let's see what we can do there. The frictional force is equal to mu times the normal force, right? Sorry, let me write what I was saying. Frictional force is equal to mu times the normal force. And the normal force, what are they asking us to find here? What value of F? The normal force and F are going to be the same, right? Because the block's not sliding into the wall or doing any other bizarro thing. So we want, making this substitution, if frictional force has to equal this and that, then mg is equal to mu times F. And that means that F is equal to mg over mu, which is C. Number 29, we have a mass suspended by a spring with force constant K, has a period T when set into oscillation on Earth. Its period on Mars, whose mass is about 1/9 and radius 1/2 that of Earth, is most nearly, let's see, a mass suspended by a spring with force constant. So let's see, how does this work? We have period is equal to 2 pi times the square root of m over k. And on Earth, this just is what it is. And here, whose mass is about 1/9 and radius 1/2 that of Earth. Well, look, what is this the mass of? This is the mass of the object that's on the spring, right? Notice that the mass of the planet, in other words, like these things would affect gravity, but that doesn't come into play here. When you've got a spring oscillating, the thing that controls that is the spring constant, right? You can stretch it out a lot, you can stretch it a little. The period's the same. What makes a difference is the mass that's on the spring, and not gravity, right? Mass is independent of gravity. These two things would change gravity, but not change the period of the oscillating mass on the spring, because that only depends on mass, and that's the same. So there's no room for either of those factors in that question. So it's just T. Number 30, a 1,000 watt electric motor lifts a 100 kilogram safe at a constant velocity. The vertical distance through which the motor can raise the safe in 10 seconds. Let's see. Remember this equation? Power is equal to work divided by time. So, if we're going to lift it at a constant velocity, work is equal to force times distance. And if it's being lifted at a constant velocity, that means the lifting force must be equal to the gravitational force, right? If it's going at a constant velocity, then the upward force on it, constant velocity means net force is 0. So that lifting force would be the same as mg, so that gives me mgd over t. And I think we got all that stuff, and that's equal to power. So let me just sketch that out here. So 1,000 is equal to 100 is the mass. Gravity, we're going to use 10. What distance? That's what we're looking for in 10 seconds. So those cancel. We divide by 100. That gives us 10. Let's see. Number 31. A 1 kilogram mass is attached to the end of a vertical ideal spring with force constant of 400 newtons per meter. Mass is set in simple harmonic motion with an amplitude of 10 centimeters, or 0.1 meters. The speed of the 1 kilogram mass at the equilibrium position, that's at the maximum speed, right, is, let's see which one of these. So if we can set this up. Do you remember that omega is equal to the square root of k over m? If you don't remember that, you can get it from the period. Remember this. Remember that period is equal to 2 pi divided by omega, and that'll get you there. But I remember this. I remember that the omega in this equation is equal to k over m. The omega in any kind of simple harmonic motion is the analog of this, right? So, for example, it would be g over L if we had a pendulum, or what other situations do we have? It could be like mgh over I, right, for a physical pendulum, and so on and so on. So that applies to all those situations. Now, we want to know its maximum velocity. We know the position is equal to amplitude, which is 0.1, times sine or cosine, whatever you want, of omega t, and that velocity is equal to the derivative of that. That'd be 0.1 omega times cosine omega t. That omega pops out because of the chain rule. And that the maximum would happen right here, right? Because this would max out like sine and cosine functions do at 1. So max velocity would be 0.1 times omega. So let's see. Let me do that down here. That's 0.1 times the square root of k 400 over m is 1. The square root of 400 is 20 times 0.1 is 2. So that's maximum velocity would be 2 meters per second. Students testing the kinematic equations for uniformly accelerated motion by measuring the time it takes for lightweight plastic balls to fall to the floor from a height of 3 meters in the lab. The student predicts the time to fall using g as 9.8 meters per second squared, but finds the measured time to be 35% greater. Well, if they're lightweight plastic balls, there's probably some air resistance, right? Which of the following is the most likely cause? Acceleration of gravity is 70%. Like, these two answers are totally insane. 70% greater, 70% less. I mean, those are like totally different planets, or like very far from Earth. Air resistance increases the downward acceleration. Well, air resistance, there's mg, and the force of air resistance would be upward, so that's actually going to decrease the acceleration, right? Because it's fighting against the downward pull of gravity, so that's not right. Acceleration of the plastic balls is not uniform. That's actually true. We know that from our, what does the acceleration look like? Acceleration starts out at 9.8, and then it actually goes down like this when you have air resistance, right? Until the net force is 0 and it reaches the terminal velocity. Plastic balls are not truly spherical. It doesn't matter. That's crazy talk. So D is the correct answer.